Okay, today's lecture is about section 16.2. We have studied last time vector fields. Today we'll study line integral. What is line integral? It's a generalization of the usual integral in one variable. We are used to integrate what? This form. We are used to do this integral f of x dx from a to b. A to b is the interval on the real line. F of x is a function of x and integrated with respect to x from a to b. Today we'll study generalization of this. Instead of integral of f of x, it is integral of f of x and y. Two variables. ds instead of dx, it is ds. ds is the infinitesimal part of arc length we are used to from chapter 13. You remember when we study the length of a curve, we used to write s for the length of the curve. This is ds, part of this length, like this. dx is part of this length of the interval. Here, over what? Not from a to b, it is over the curve c. So we have a curve in plane or in space, curve C, given parametrically by this parametric equation, x function of t, y function of t, or in the vector form as like this. You remember the vector form of the helix and the circle and this stuff, or even the straight line. The straight line is a special case of the curve. Okay, with constant direction. So when we have a curve, x is a function of t, y is a function of t, maybe z as well is a function of t, we can write the position vector of the points of this curve in the form of this vector. X of t, comma, function y of t, comma, another function z of t. This example is for a curve in 2D in the xy plane. So we're going to calculate here. We are going to calculate this line integral f of x y ds. What is this? It is an integration over a general curve, not over x on the x-axis straight line. No, this is new thing for us. It is integration over a given curve. So think of this function as a roof function. This is the heights for some, the function z, function of x or y. At every x or y in the domain, in the xy plane, we have a specific height for this function. So it draws a roof for the surface of this function. Okay, this is the idea of this lesson. It is called line integral. It is a generalization of the usual integral we are used to. Here we used to calculate integral of f of x dx from a to b, which calculates the area, okay, provided that this function is positive or non-negative at least. It gives the area between the curve of this function and the x-axis from the line x equals a to the line x equals b. Here we have the same story, but it is not over the x-axis, it is over this curve x of t, y of t, parametrically, or r of t vectorial in the vector form. So we get the same story, we get the same conclusion. We calculate the area under this roof surface and over this curve in the plane or in space. But the situation here is a very strange fence. Like the curtains, it increases, decreases, and curves over the value of the variable t. T is the parameter we have here, x function of t, y function of t, t from a to b. So this is a curve in xy plane, as you see. So what is the formula for calculating this? The same story of line of integration. We take infinitesimal part of this curve, call it ds, and calculate ds. We know the formula for ds. We proved it in chapter 13. to prove a formula for the arc length of a curve. It was given by this square root, this big square root, x dot square plus y dot square dt. Why is that? Remember that it is, if we take infinitesimal parts, if we take very small, tiny dx and dy, we get very tiny ds, or vice versa. If we take very small part of the curve ds, we can take this horizontal and vertical parts dx and dy, we get something like a right angle triangle. Dx and dy are the legs of the right angles. So ds square equals, by Pythagoras theorem, as you see, dx square plus dy square. Therefore, ds by dt equals the square root dx over dt, like the derivative, rate of change of x with respect to t squared plus rate of change of y with respect to t squared. It's like the components of velocity, if you remember. So this is the ds thing. So go back to the formula of line integral. We have a function of f of x dx. No, this is the original integration we are used to from secondary school or high school. Here today we have this. This is the generalization over some given curve. We are given the function, we are given the curve over some parameter on some interval of the parameter. The parameter varies from t equals a for the initial point of the curve up to t equals b, the final point of the curve. So we get this formula. If we substitute for x, y, and y of x is a function of t given, y is a function of t given, and this is the ds. ds is this big square root of r dot square, modulus r dot square, if you remember this notation, if you like. So let's take some example. Think of this function of two variables, x, y. This is defined everywhere. In fact, no problem at all. No division, no logarithm, no problem at all. So the domain of this function is whole of R2. And Z is the height of the function. But notice that this may be positive, may be 0 if x or y equals 0, may be negative if exactly one is positive and exactly one is negative of the two variables. And let x be cosine t, y sine t, and t moves from 0 to pi over 2. So I think you know this curve very well. It is a part of a circle. This is a part of a circle. Why is that? Because x squared plus y squared gives cosine squared t plus sine squared t, which is 1. So we get x squared plus y squared equals 1, which is circle. But we don't deal with this whole circle. We are given this condition. So we are asked to deal with a curve, part of this circle, which part of the circle? It is the first quarter, where from t equals 0 up to t equals pi over 2. It is when t equals 0, you see the point 1, 0. Cosine 0 is 1, sine 0 is 0. When t is pi over 2, cosine pi over 2 is 0, sine pi over 2 is 1. So you go this part of the curve. And we have put this arrow here to show the direction of the curve. This is the initial point, and this is the final point. So we are asked to do the integral, this line integral over this curve. This is what we call line integral, as most of the books call it line integral. Some of the books say it is curve integral because it is of an integration over a curve, not over a straight line. Of course, line is sort of curve. So no problem with the name. The idea is the most important thing. So now this ceiling function or the roof function, here z equals product of x and y, we need to integrate over this curve. What we get, as I mentioned here, we get this area of this fence or of area of these curtains. Why you study this, by the way? This is very important. It has many good applications, actually important applications. These application is used for these curves and these areas, and this stuff is used in the industry of planes and industry of cars and other stuff. So we need to find this integral, this line integral, f of x, y, ds over this curve C. So what to do? So we use the parametric substitution of x and y and ds. So as you substitute for x, plug in the value of x, cosine t, the value of y is sine t, the value of ds we need to calculate as usual. ds is the square root of the rate of change, squares of rates of change, or the magnitude of the vector v. So we need to differentiate x with respect to t as usual. It gives negative sine t. Here, derivative of y with respect to t, it gives cosine t. Square all of this, square this, and square this, and add them, you get 1. So the square root here, this big square root gives you 1 here. And dt. So this curve integral or line integral changes into usual integral over interval, normal interval from a to b. So what we get, this is instead of the value of x, instead of the value of y, this is instead of the value of ds. What is ds again? ds is this tiny part of the curve, like the dx in the calculus 1 story. Calculus 1, we have dx here on the x-axis. Now we have for this line integral, for line or curve integral, we need the equation of the curve. We need to evaluate this value of ds. And then the rest is straightforward. What happens then? You calculate this integral. You have many ways to complete this integral. You have use this. You can consider this as u, cosine t is u, and you have its derivative here, but you need its some sign here inside and outside. Or easier not to, if you don't need to put negative sign inside and outside, use this sine t as the u substitution. Plug u instead of sine t. So du is this cosine t dt. So we have u du, we get half u squared. What is u? It is the sine t. If you need to put it in details, you need to do this. U equals sine t. Therefore, du is cosine t dt. Therefore, this is u, and this is du. Integral of u du is what? Half u squared. And I do the substitution quickly because it is clear and easy. It gives half u squared. What is the u? It is sine t. Use this substitution, make it easier because we don't need to put negative signs. Then the t varies from 0 to pi over 2. Use the fundamental theorem of calculus. Substitute, plug in this upper bound minus substitution of lower bound, you get half. What is this half represent? Geometrically, it gives this area. Is the area over this curve and under the surface of this function. Call it the area of the curtain, the area of the fence. So it is curving, it is high at some points, it is low at some points. Like think of the curves on the front part of the car or planes or this stuff. This is the idea. Geometrically speaking, this is what we have. We have this part of the curve C, which is quarter the circle. And we have this Z function, the Z function of x or y. It is in third dimension, which is a equal xy. So its value is 0 at this point and at this point. And then it is up and down at the other points. We get these strange curtains or strange fence. Okay, this is the integral solution in details. You need to give your detailed solution of the integral. You can do it quickly like this. You have the right to do this U substitution in your head without doing it explicitly. If you are not familiar with doing the U substitution quickly by this way, you do it in details. You put U sine t and U is what, and change even the upper and lower bound of t into the upper and lower bound of U. You can do all of this. Do it anyway, but you need to show your work. This is full mark for this, full mark for this, as you like. I prefer you practice a lot integration and this mix of integration in the coming weeks and days to prepare for the final exam, inshallah. So this is the area of the fence. This is the first part of today's lecture, to do this curve integral or line integral ds instead of dx. Here s, here curve. Here we do this. We don't write s here, we write c. C for curve. Given curve. Given what? As a function of t parametrically. T may be any parameter. The arc length may be the angle, may be the time, whatever. So this is the first meaning we have for today. Area under the fence. As usual, area under the curve of the function. But today we have a function in two variables. We can okay, we finished this. Think of this curve here in 2D. This is the curve in 2D. And this is the function z, function of x or y, the height of the function in the third dimension. C is given this way as a vector, x of t, y of t, and so on. We have other examples. I will not do this in details, but I read it with you. Find this line integral or curve integral. This is the function of x, y, and this is the s infinitesimal part of the arc length. C is the right half of the circle x squared plus y squared equals 16. So it is the right half of the curve of the circle x squared plus y squared equals 16. Of course, you know this is a circle. This circle is with center origin. Origin is the circle, and its radius is 4. The right half, as you see, it is in quadrant 1 and quadrant 4, where x is positive, x bigger than or equal to 0 here. We begin from down there at the point of the 0, -4, and go up to the 0.04 up in the on the y-axis. Of course, we can parameterize this. We can parameterize this circle using x equals 4 cosine theta and y equals 4 sine theta. This we get rid of this 4 and take this form. The C is, the curve is given by R of t given by 4 cosine t is the x value and 4 sine t is the y value. For this, when t equals -pi/2 up to pi/2, why I take this interval down there, here, on the negative part of the y-axis, the angle is this. the angle is theta equal negative pi over 2. Here up there, the angle is theta equals pi over 2. So to take the domain as an interval from the negative part of the y-axis, y negative, up to y plus, we go from theta or t equals from negative pi over 2 up to pi over 2. So the integral again is, we substitute for the x to be cosine t, y to be sine t, and ds is, we need to calculate ds as in the previous example. Again, once more, r dash equals negative 4 sine t, 4 cosine t. I differentiated the x with respect to t, differentiated the y with respect to t. Calculate x dash square plus y dash square, or x dot square plus y dot square. Or the magnitude of r dash square. This is the same. It gives 4 at the end. Because of the cosine square plus sine square is 1. So it gives 4. Square root of 16 is 4. Or directly. We have here a bit more difficult situation because we have the cosine and sine power 4, but it is not that difficult. We can use the u substitution again. The good substitution is to use t equals u is sine t. The derivative is here, and I leave it to you to complete this integral. Is this value. Okay. If the curve is formed of the union of many curves, we can go piecewise. We integrate over C1, part of the curve is the first part C1, then plus the integral over the second curve plus the integral over the third curve. Here he explains the example for us. This curve formed of, or the path formed of, the union of these three pieces of curves. Maybe line segments, maybe curves, whatever. We move on each curve or part of the curve and substitute for the parametric form of this curve and compute the integral as before. So let us think again, and we are given this function of two variables, x and y, and he asks us to integrate it over this curve C formed of C1 union C2 union C3. What is C1? Part of the circle that begins at 2, 0, 2, 0, 2. This is quarter the circle. Okay, then C2 come back along the y-axis to the origin. So this is a line segment. So the situation is this: 2, 0, 0, 2. Here we have part of the circle like this, C1. And then come back along the y-axis. So C2 is this part. Come along the y-axis to the origin. This is the origin, 0, 0. Third part, along the x-axis to come to 0, 2 or again. This is the part, C3. So the curve here we are talking about is the union of this curve. So it's a closed curve, C1, union C2, union C3. So how to do the integral? We have to partition the integral into 3 integrals. The first curve integral or line integral over this quarter of the circle, like what we have in example 1. Look here, this is quarter of the circle. See, here is the C1 we have now. Then another integral over this part. How to do the integral over this part? We need to do the parametric form of the curve of this line segment. It is the straight line here, x equals 0, but from y equals 2 up to y equals 0. We need to put it in the parametric form. Again, at the end, we need to do the third integral over this part of the curve C3. What is the equation of the curve C3? It is a line, straight line or line segment, part of the straight line. It is y equals 0. And x varies from 0 up to 2. Okay. What is required is to find the area of the weird wall, this fence, very, very strange fence, or wall or curtain built on this path C. C is this curve, piecewise defined curve, union of piecewise defined curve. To meet this roof or ceiling, that's it. This is what I explained here. And I think it's easy to do. I leave it for you to do, to practice. This is the curve form of C1 here inside and C2 here on the y-axis, then C3. It is not required to draw these surfaces, but I am explaining here. So the integral here is the sum of integration over C1 plus integral over C2 plus integral over C3. And we need to do each one of them in details. The first one is very similar to example 1 we done before. This is the ds, this is the 2, this is the part of the circle, it is the quarter of the circle. The radius is 2. The point is 2, 0, the point is 0, 2. This is C1. We write the equation of this curve in the parametric form or vector form and calculate this ds. The rest is straightforward. C2, what about C2? We can write the equation of this straight line going from 0, 0 to 0, 2 and use its direction. The direction vector here is this vector. It is the negative j. You may need to use this equation, the vector equation or the parametric equation. R equals a point on this curve is 0, 0 plus what a vector on this direction. The direction is from this 0, 2 to 0, 0, which is negative j. And t. Let's write it in the other way. This is the parameter t times the vector here is 0, negative 1. This is a point on the line. This is a vector on the line, point, and this is a vector on this line. Therefore, x equal, here r is the xy. Therefore, x is the first coordinate, 0 plus t0, so it's 0. We know this. The y-axis has Cartesian equation x equals 0. And y is, the other part, 0 times plus t times negative 1. So it's y equals negative t. If we use this is right, and this as well is right. If you use the point on the curve is, instead of 0, 0, if you use the point 0, 2, you come to the same conclusion because we can write any point on the line here. Again, we calculate ds for this situation. The dx is 0, the dy is negative 1. So we can finish it easily. The third on the second wall, and then the same for the third wall. Again here, the third part of the curve is this C3. From the point 0, 0 to the point to 0. Of course, this is the x-axis. The equation is y equals 0. And x varies from 0 to 2. So you can use dx directly as that instead of ds. And you can use this detailed form. Or you put here any point on the curve, 0, 0 is there. And put this direction, vector I in this direction. So you can put t. This is the parameter, and any direction here, I is 1, 0. This is I, 1, 0 vector. This means xy equals 0, 0 plus, we can add them directly. So it's t, here we get 0. Therefore, x equals t and y equals 0. This is the parametric form, and t varies from the smallest value of t is 0, the biggest value of t is 2. Why is that? Because x is t. So therefore, we have ds equals square root of dx dt all squared plus dy dt all squared. This is clearly dx dt is 1 plus dy dt is 0. So we get 1, and ds is here dt. So it's 1 dt. As expected, of course, because we are on the x-axis. Therefore, integral over curve 3 is t equals 0 up to t equals 2. Here is the function. Where is the function? X plus y squared, whatever. ds. I leave it for you to finish it. Very straightforward after this. This technicality of the parametric equation of the curve, straight line, we are used to even in 3D. We wrote this equation many times. The equation of any straight line in space is given by some point on the line and some vector along the line. R equals P naught, any point on the line, plus T, the parameter, here V. This is in 2D, in 3D is the same. Any question for this first part? We solve it in details, all of this. The second part, when we have what? Line integral also. We studied this line integral over the curve C. C is curve. But we have another situation where we have vector valued function. We studied last time the vector valued functions. What is called f of xy. Vector, you input a vector and output a vector. So now we have to integrate a vector valued function, capital X, over some curve. See, the definition is by dot product. Look here for f any vector function. If this function is a vector valued function, f of x, y, vector field, I mean, think of what? Think of velocity field or force field, a magnetic field, gravitational field, whatever, electric field. It is a vector valued function. And ds here, this is ds as a vector. If this is a vector valued function, so we use this ds as a vector. So, and this is the dot product, dot or scalar product of two vectors. Same situation, we are given a curve parametrically, x function of t, y function of t, or written in the Ij notation, and the parameter varies from a to b. And this curve is a 2D curve like this. This is the initial point when t is a. This is the final point when t is b. This is the explanation of the derivative of the vector valued functions. We are aware of this from chapter 13, how to differentiate the vector function. Differentiate it piecewisely, pointwisely. Differentiate the x plus differentiate the y. And what is this benefit for? What is this means? We calculated this before in the first part and said this means area of the fence or the curtains. Now here this means, in fact, the work done by this force field. If this is a force field of some force, and this is ds, little displacement, so we calculate the force dot the displacement in infinitesimal part, we get the work done by this force to make this small displacement. And the integration means add all of these infinitesimal parts or pieces of work of this force over this curve. So this is a very important physical meaning, which is the work. We are used to this for constant functions, and in the same direction of the displacement or in the opposite direction of displacement or making some angle with displacement, we are used to this to calculate the work done by this force to make this displacement by multiplying the component of F along D, or to compute the dot product of F with D as dot product of vectors, scalar product of vectors, which means we get a scalar quantity, which is the magnitude of F times the magnitude of D times cosine theta. This is F dot dd, dot D. F dot D, as you know. This is very important. So the generalization of this we have today is, we are used to this formula before. F dot D calculates the work done by this force to make displacement vector D. For the vector field, the force is not constant. Even D is not constant. So how to calculate the total work done by this force field to move an object from this point on the curve to move along this curve up to this final point on the curve? Think of F as force given by some component along I, some component along J, like this. F is simply P function of X or Y, Q function of X or Y. This is a force, variable force field. At every point, it changes. Maybe XY, maybe X squared Y, maybe sine X, Y squared, whatever. It moves, it changes at every point, it gives a different value. When we move this particle on this curve, this force field makes some work. So how to calculate this work? We do this dot product, we do this line integral over this curve again and again. This is curve C given by R, X function of T, Y function of T. Maybe a circle, part of a circle, line, many pieces, C1, C2, C3, maybe this curve. What is the amount of work? What is the value of the work done by this force to move a particle from here along this curve, then along this curve, then along this curve? The value of this work is the line or curve integral of F dot dr. Dr here. This is the line integral for a vector field. So we need to use dot product, and the meaning is very important. It is the work. This works for electric fields, magnetic fields, gravitational fields, velocity fields of motion of liquids. Liquids may be water in the ocean, air, and so on. So this is very, very important application of the new type of integration we're studying today. So we zoomed in a little bit and calculate this F dot dr. So it is dW, d work. Notice that this tiny part of work, when added, means integrate, gives total work. Notice that what the work is a scalar quantity. Although the force or the velocity is a vector, the displacement or the position vector is of course a vector, we get the value of the work is a scalar quantity as known from physics. We're studying all fields of physics. This is an important scalar quantity. This is dW, and then at the end of the day, the total work is this F dot dr. How to do this? We will be given this force field or any vector field, and dr is dx, dy, and we can write it another way. So assume we have this situation, a given vector field, P and Q, simply P and Q. dr is dx dt, dy dt, all dt. How to do the dot product? We know this. How to do the dot product? We multiply the component of I, the first component, with the first component, plus second component with second component, and don't put I or J or this stuff. It is a scalar quantity. We know the product of two vectors, the scalar product of two vectors. This is not cross product. We will come to cross product later in other types of integration. So this is how to calculate the work of a vector field over some curve, which is, as you see, a nice looking formula. So let's have some example. Think of this. We studied last time how to sketch, how to make a sketch for such a vector field. At some points, let's remind you. With 2 points, say this point is 1, 0. Think of a particle on this field, and it will be kicked by this force in this quantity. So the input is the vector 1, 0, or the x is 1 and y is 0, and the output is this vector y in the direction of I, so it's 0 and minus 1. So f of, for example, therefore f of 1 or 0 is the vector. So this function makes what? This function brings the y in the direction of I and minus x in the direction of j. So it gives this 0 here and takes this 1 here and make a negative sign. So it gives minus 1. So it is the vector 0, negative 1. Where is the vector 0, negative 1? It is minus j. Minus j vector at this point is this kick. So this point 1, 0, if the particle is at this point 1, 0, it is given a kick or displacement minus j. Yeah, it means a vector of magnitude 1 downward, like the vector of gravity downward. and so on. We are not asked to sketch this vector today. We done that last time. Now, where is the curve you are talking about? It is again the part of the circle or the whole circle now. It is the whole circle because this is a full revolution from t equals 0 up to 2 pi. As you see, cosine t, sine t, this is the whole circle. If this is from 0 to pi, we get half circle and so on. We studied many situations of the circle. The whole circle, the upper half circle, the lower half circle, the right half circle, the left half circle, and the quarters as well, and so on. So the parametric form of this R of t is cosine t. This is the first component or the x component or the I component. The sine t is the y component, the j component, the second component, and this is the value of the parameter. And so we calculate the RDT as usual. We get these usual derivatives and we get this circle. It's not nice looking circle, but we can do it better. Okay, let's do it this way. That's better. Yet, that's better. And so on. It begins here. When t equals 0, we get 1, 0. When t equals pi over 2, we get 0, 1, and so on. And the direction is this direction. And continues, full revolution to come back to this initial point is the final point. So it's a closed curve as you see. This is the position vector of the curve, the equation of the curve given by parametric equations or vector equations, as you see. So what to do now? Calculate the work done by this force field, or maybe written another way, find, maybe written this way. See, or do this closed circle because the curve here is a closed curve, f dot dr. Maybe written another way, y dx plus it's not plus, it's minus x dy. Why is that? I performed this dot product. This dot product gives, this may be given with the vector form, with the bold vectors and dot product sign, or the dot product may be performed and given in this linear form. Okay. Now we do this dot product of the position vector of the curve with this vector field. Where is the vector field? It is given here. Y in the direction of I minus x in the direction of U. This is the P and Q we spoke about before. So where is the F? This is the F minus Y minus X. Y in the direction of I minus X in the direction of G. Plug in the value of the Y on this curve. On C we have what? F is, plug in the Y value of Y on this curve. It is sine t. Plug in the value of X on this curve. On C, X is cosine t. So it is sine t minus cosine t, or use the vector notation sine t minus cosine t. This is the force field in this question, or vector field in this question. Dot product this with dr. What is the dr? We already prepared this dr. What the dr is here? dr is this derivative times dt. So 1, 2, 1, 2 gives you f dot dr. This is f dot dr, multiply what? First component cosine t with this component sine t, plus second component cosine t with minus cosine t. you get this. This is the first component times first component plus second component times second component. And this is the dt. Where is the vectors? Vectors are gone. No vectors anymore. These were the vectors. Here, these notations have the vectors on. When we perform this dot product, we get a scalar quantity, which in fact means the work by this force on this curve, to move a particle on this curve in this direction. So we get this value, and here we have the value of the interval, the parameter values from the initial point to the final point, t from 0 to 2 pi, to move it around the circle, full revolution, t equals 0 to t equals 2 pi, moves until we get back to the same point. So it's a closed curve. Okay, perform the computations and the integral. Here we give sine t times minus sine t, we get minus sine squared dt. Here minus cosine t times cosine t minus cosine squared dt from 0 to. What is this? Okay, we have this usual identity, the basic identity, cosine squared t plus sine squared t is 1. So we get minus 1 here because this is minus 1 as a common factor. So it is minus 1 dt. Minus 1 dt from 0 to 2 pi is minus 2 pi, of course. How to do? This is usual integral. Integration will be t. T from 0 to 2 pi is 2 pi minus 0 and minus 1 outside, so it's minus 2 pi. The important thing here is this negative sign. It means something. It means that it is a negative work. The work done by this force to move this particle in this direction is a negative force. Why is that? How to expect that? Okay. Look here at this force field, the part of the force field we sketched here. This force needs to take this particle down, but this curve is going up in this direction, like something moving on this track. But this force is resisting, it pulls it down. So it does a negative work. It is resisting force. This is the physical meaning of this negative sign. This force opposes the track, the track C, the movement on this track. Okay. I think we stop here because of our time.